Thanks everybody for coming. And good afternoon. I hope you had a good lunch. Hope you're not too full. We don't want to put you to sleep. My name is Brad Kennicott. I'm the project leader. I'm an MFET major. On our team we have Joe Kamens, he's the executive secretary, Jake Bailey, he's our quality planner, Michelle Holmgren's in charge of documentation, and Treston's the treasurer. But in addition to those duties, we're a smaller group, and so we've worked on the whole project together. Everybody's designed parts, everybody's created drawings, everybody's worked on cost estimate. As the presentation goes forward, you guys will note that. Today in our presentation, we're going to talk about the scope of the project with an executive summary. We're going to talk about our schedule that we've held ourselves to, our design requirements given to us by the customer, the research that we did, and we'll talk about the design that we've come up with and our accounting of the money spent. Okay, so in this project we were tasked with designing a new hand-operated injection molding system that's used in the plastics class here at Weber State, taught by George Comber, who is our customer. This machine uses CNC machined molds that we use our mills to make with an injection port and runners and a simple design. Some of the problems with this machine and complaints from the customer included how easy it was to load the machine, because there's two problems when you go to load this machine. You've got to worry about your orientation of your hole in relation to your nozzle here, and so when they have a thicker piece of material, they'd have to shim it to get it to sit where it needed to sit, and your orientation side to side to line it up. One of the other problems with that is, as you can see here in the picture, this thing, the plastics that we were using melt for anywhere from 300 to 450 degrees. And so when they went to go load this is very hot, and there's heat radiating off here, and then you go to pour the plastic in, and you shove it down into the bore with many times a popsicle stick, as you can see here in the photo. And so it's not very safe. People could get hurt, burned, and so that was another thing that we were looking at. Let's see here. We were tasked with building 2 of these machines by fall of 2010, and we were given a budget of $500. Joe's going to talk a little bit about our schedule.
Thanks, Brad. I'm Joe Kamens. I'm the executive secretary of the group. As part of that, I was also in charge of the schedule. We started the semester, we decided to have a few goals of what we wanted to accomplish, and then we made our schedule around those goals. So for the first semester, which is what we've done here, and we're presenting, we started out by researching our subject, seeing how injection molding machines work, different designs, what's going on. We looked at this machine, saw what we might be able to change there, came up with a few ideas. From there we went on to doing a bench test. We wanted to try a few ideas, see if what we changed worked or not, see what our initial ideas would give us. We went on to produce a design that we have for you today, and also a cost estimate that we will show. We also set our goals for next semester also. What we're going to do when we start next semester is we're going to purchase our material and make a quick prototype so that we can test our design, see what's going to go on. We were planning on revising it. We know there will probably be changes made, and hopefully we'll also be able to make an even better machine from the data we get then. And we will use that to make our final project. We are on schedule right now. Nothing's been pushed back, and we're planning on staying that way. So we're going to go back to Brad.
Okay, so like I said, this is the machine that we based some of our ideas off of. But like I said, George and the plastics part of the school is our customer. And George gave us another idea of, and we're going to call this the Hansen design. It's from Rodney Hansen, and I believe this was from his engineering magazine. And he's got completely how to build just a home version of one of these. He's got a parts list and everything in here. So this was a good help to give us some more ideas on how we could improve this machine. Some of the features that this first machine has is a vertical design. The mold is beneath it, and you inject down. It has a half-inch barrel size with about a 0.86 ounce shot size. The footprint of the machine, as you can see here, is fairly small. It doesn't take up a lot of space. Where in the Hansen design, what you see here is it's a horizontal design, and it's got the barrel here, and it would clamp the mold here, and it would shoot forward or towards the operator. It would shoot. And its barrel size is 5/8 with a 0.99 ounce shot size. And the footprint is it takes up quite a bit more space on the bench. In talking with George, he gave us a few requirements that he would like us to base our design off of. First was he wanted a 5/8 nozzle with a flat face. And the reason for that was when you go to machine out this, where the nozzle interfaces, he wanted it easier to make, so it would sort of less machine time, less tools needed and stuff like that, and just make it easier. He suggested that we use 4140 steel for the barrel and nozzle as material types. And he also wanted to make sure that it was mobile, so the semesters that the class wasn't being taught, the machines could be stored away. He wanted us to be able to inject polypropylene, polyethylene, and polystyrene. I'm going to turn the time over to Jake to talk about some of our research.
My name's Jacob Bailey. I was in charge of quality planning, and one of the first things I did for our quality planning was to make sure that all the parts and everything we designed, all the drawings were at least checked by 2 people in our group to make sure that each drawing had tolerances on it, and also to make sure all of the dimensions were on the drawing that were needed. Another thing that we did was to develop a survey to test what the customer wanted for a new injection machine. And from that survey, we also did the bench test. And from the bench test, there were a couple things that we wanted to learn. The first was what heating element to use. We had a decision between heating band and heating cartridge. And we decided to go with the heating band because the cartridges were at least double the price of what a heating band would be, because we'd have to have 2 to 3 cartridges to heat the barrel. We also chose the heating band because of maintenance reasons. It would be a lot easier to change a broken heating band than it would to try to pop out some cartridges that were press fit into the barrel. The second thing we wanted to focus on was the fit between the barrel and the plunger. We looked up in the machinery handbook, RC4 fit for close tolerance with machinery parts. We chose that so that when the plunger goes down into the barrel, that we wouldn't have backflow from the plastic inside. Another topic we wanted to focus on was the material type. As we mentioned before, George wanted the part to be made out of 4140. We decided to see what a different material would do, so we went ahead and went with aluminum. If you look down here, this is what our bench test looked like. Show this up. The heating band's on the bottom with a thermostat here, and the barrel and the plunger. And with the aluminum, we also wanted to see how the heat would transfer throughout that whole part. Another thing we wanted to focus on was the shot size. With this machine, it has an ID for the barrel of 1/2 inch, and we were wondering what a bigger barrel ID would do. And we went ahead and went with a 1-inch ID barrel, and we also wanted, and from that 1-inch ID barrel, we wanted to see how the plastic would react to the heating, if it would melt all the way through, or if it would scorch and degrade the plastic. And I'll turn the button. Yeah, I'll turn my time over to
Okay, I'm back up here now, I guess. Oh, we performed a bench test. We'd like to let you guys see what it was like.
Here we go. Four. Is that hard to pull?
No.
Oops. No. I still.
Not necessarily the desired result.
No.
No, but you learn more by failure, right?
Sometimes.
I hope we did. You can tell there one of our big issues with our bench test was our clamping force. We kind of looked at this as a couple parts. First one area we looked at was the nozzle design and how we're going to address that with clamping force. Our customer requested a flat nozzle design. It's easier to machine, easier to make, produce in the mold. So we went with that, and we found out, compared to what we were doing, we need to have more of a force, clamping force holding against the nozzle so that the plastic doesn't come out over the top of the mold. And that also goes along with the fit of how the barrel fits in with the mold. And also, the other clamping force that we dealt with was how we hold the mold together. We only wound up with flash on one of our runs, so we think we're going to be okay with just a standard vice clamp style, producing the clamping force to hold the mold together. The second area we looked at was the pull force of the lever once again. We really want to make this easy for a smaller person to use. We don't want to have a big brute like Brad have to come in to make this machine work. We just want anybody to be able to use it. When we did the test, we found it uses a 10-pound pull force. To pull down, it was actually quite easy on the runs that we did where it injected. 10 pounds would be plenty fine. Off the calculations, that equates to an 80 psi pressure inside the barrel when you're injecting. Number three, we wanted to address this. Both designs, they had different diameters in the nozzle for the injection. The design, the Hansen design that we used for research, it had a .078 inch diameter hole in the nozzle to inject with. We started down there because the other diameter was a little bit bigger, and we want to start there so we could drill it out and move bigger. We were having a hard time with the plastic freezing inside the runners at that diameter, so very quickly went to the bigger diameter, and that worked quite a bit better. We didn't have any freezing problems, but it did show us another problem that we were running into, and that is the thorough melting of the plastics. We, several times, you can see in the examples here, as you look into the runner system, you can see unmelted pellets inside the runners, plugging the runners. So there's a couple things that we figured out. Well, that was great. You want to pass it
Yeah, I'm
on?
gonna pass a couple of these examples around so you guys can see.
The first one was patience. Carrie always thought that one was pretty funny whenever we said that. It became a big joke for us. But it seemed like the longer we waited, the better shot we would get. It correlated with that is the barrel diameter. We were noticing that with the unmelted pellets, those tended to be on the inside, in the middle of the barrel. And like the finish, the full injected part there, you can see how the plastic's a little bit burnt. That's coming because the diameter of the barrel is so big. It was burning on the outside and not melting on the inside. Another thing that we noticed, there was a bit of a heat sink. We did the test on an arbor press. We had an infrared gun testing the temperature, and we could tell that there was a big heat drop, and actually the heat was being pulled into the arbor press. We separated that with a couple pieces of wood, and that seemed to work out and help us a lot better, and that was all gone into finally, the last thing we really addressed from the bench test is the D factor. It's not a Bug's Life thing, but it actually comes from our very own Brad Kennicott. He's an inspiration to us all. He has a tendency of touching very hot objects. We repeatedly,
Multiple
every
times.
Yeah.
What was that?
Multiple
I
times.
never
Well-
learned this lesson.
With warnings. So we wanted to incorporate in our design some safety features, keeping people from getting their hands in there from burning themselves. And so we'd like to turn the time over to Michelle for a little more on her research.
My name is Michelle Holmgren, and I was assigned the documentation for this project, which includes assembling the final documentation for this project. And some of the things I did for that was to set up an account on our space so that our files could be accessed from any internet so that we could all work on the project when we could. And I also developed a file structure so that we knew what was in each of the files when we could share files with each other. And I produced a drawing template for the quality planning, and I helped organize the binder at the end of the semester. Okay, like what was talked about, we did send out a customer survey because we wanted to know what the customer wanted in the new design. So we sent it out to George Comer, who is the professor for the plastics class, and also to many of the students that have taken the class and have used the machine that is in the lab right now. And this customer survey includes questions such as how easy is it to mold, put the mold into the machine, how easy is it to pull the shot, and such questions as these. And they were ranked from 1 to 5, 1 being poor, 5 being excellent. And we used the responses from these students and the professor to take the average of their rankings, and we put the average into our house of quality. We did house of quality so we could define which design features would affect each of these customer needs and what we could focus on in our design process so that the machines would actually be better in the end. And here on the side are the customer needs that comes from the customer survey. And here up on top, not sure what I did, sorry. Here is the design features that we defined as a group, and they include such things as the heat sink, or in actuality the elimination of the heat sink so that we could keep all the heat next to the barrel, the hopper, the bore size, and all those other design features. And as we looked at the results of this house of quality, we noticed that 3 of the design features were really important to focus on. And these design features are the heat sink, the bore size, and the lever. And recently we spoke with George Comer, And he also suggested that we focus on the hopper design as well, as that is also important to our design. So first of all, the thermal transfer in the machine. Thermal heat is very important to an injection molding machine in order to melt the plastic and inject into the mold. So we wanted to keep the heat next to the barrel and not going out into the hopper or to the frame, because that would cause problems. And we wanted to keep it near the barrel so that, like Joe said, all the pellets will be melted. When we were researching the heat transfer, we looked at Fourier's law, and I don't want to go into too much detail about this because I'm sure most of you know more than I do. But we looked at the equation, which is right here, and that includes the K factor of the material, the area across which the heat transfer will transfer, and the material thickness. And each of these will pretty much be the same. What we were going to change was the material, and what would influence the heat transfer of the material is the K factor. And the aluminum, which is the material we used in the bench test, has a really high K factor. Right here it's 250, and so we noticed that it really did transfer the heat out away from the barrel. We wanted to go with something more like carbon steel or stainless steel, which has 43 and 16. Next is our bore size, and the bore size is important in how the pellets melt as well. Here in these images, we can see the top image is from our bench test, and the bottom is from our new design. How the cross-sectional area of the bore allows the heat to transfer, to stay in the barrel and melt the pellets without burning the outside and leaving the inside unmelted. Next is the lever system, which was also mentioned, how we want anybody to be able to use it in shooting the mold. And we wanted to keep it a one-piece lever, a solid design, so that, because in this case, this uses a cheater bar, which can be taken off, and we wanted it to be a solid design so that the cheater bar won't be lost or used for some other reason in the lab. Now we'll turn over the time to Tristan to talk about accounting.
Good afternoon, my name is Tristan Sadler. I'm the treasurer for the Injection Perfection. So one of the jobs for my treasurer assignment is to account for the money that we're spending. Going back to the bench test, we only spent about $50 on the electrical components. So that's going to change next semester when we start buying more parts and spending more money. That's where we're at right now. We were given a budget of $500 from George, and we decided to see if that was the right amount of money. We decided to do an estimate. So we came up with what you see here, the bill of materials. So we've got the material, the quantity, the size, and the price. And that came up to just over $800. So it was a rough estimate. And then this is the final design, what it would cost. We came up with that to be about $1,543. So, and that does include the labor and the overhead, and then the materials cost. But then the final estimate, or the cost after donation would be about $200. So, now I'll turn the time over to classes.
Okay, so now that we've talked about all the efforts we went through on research, we really spent a lot of time on research because we didn't want to have to do redesign and spend all that time with rework. So, and we've talked about the accounting and money spent. We want to talk a little bit about the design that we've come up with. Then, like I said, we've all worked on different parts of it. So this clamping system is the part that I worked on. A few of the features in this clamping design are a quick adjust clamp. This piece right here is a nut that is riding on a pin that can flip up, and you can easily move the movable clamp back and forth to adjust for different sizes, thicknesses of the mold. The whole system is mounted on a linear bearing. This is a bearing that rides on the extruded aluminum. These bearing slide pieces are made out of UHMW, which I've seen in industry used a lot for guides and for wear plates and different things. So, and I've actually seen similar bearings like this used. It has a camming system because we talked about that force to offset an equal force for it being pulled down, so that we don't get a flash or plastic coming out of the top. So it all goes into the mold, and so this it's on a cam with 4 cams for it to lift up evenly, and it rides on these little rods to keep it all level and even. And so you'll pull that, and then it'll push the mold up against the nozzle. Okay, so Jake's going to talk a little bit about the parts that he designed.
One of the parts I designed was the barrel. We decided to go with 4140 material, and we made the barrel IB 5/8, so we came with a total fluid ounce of about 1.2 fluid ounces for that. We also decided to go 7 inches on the length of that barrel, and to stick with the heat band, and the heat band will be attached right to the end. Another part that I designed was the nozzle. We decided to go with a 0.82 diameter ID hole. It's kind of similar to the one that's on this machine. And also to go with 7/8-14 fine threads on the outside of the nozzle. I chose the fine threads so to make sure that the plastic, when melted and injected, won't flow out through the threads. And the plunger here, we decided to go with the RC4 fit because it worked with the bench test. It should work with our final design. And the plunger is about 12 inches in length. And I'll turn the time over to Joe.
Thank you.
I worked on a couple of the different systems on this machine. First one I like to talk about is the clamping system. Basically, what holds everything together, the frame to the barrel to everything. A couple of key features to it. We decided to go with a 304 stainless steel, just for the heat transfer, to keep the heat in the barrel isolated from the frame. It fits the capabilities of us to build it. We had some design made up, and we got looking at it, the cost was too high, or we didn't have the capabilities of making it here. So what we've done here is where we hold the barrel, we have a split collar that's welded onto a couple arms that come back and attach with our frame. That makes it very easy for maintenance or for cleaning if we need to get it into the machine and do anything like that. Very quick and easy. Up on the top, up on the top here. Oh, yeah. There we go. That's the button I want. We have a plunger bushing, which is what locates the plunger. So as we move it up and down, we actually pull it all the way out of the barrel to inject the plastic before it's melted. And so that lines that. And then I also worked on the lever system and the whole design. The trick that we ran into was needing to get that plunger to move vertical. And we did that with a little cantilever system. And we slotted it right there, so as the arm swings an arc, the plunger is able to move vertical. And we'd like, also, it was out of stainless steel also for the heat transfer. It worked on a 20-pound pull force, and that 8-inch plunger stroke is what pulls it out of the barrel. So we'd like to move on to Tristan with his parts.
One of my assignments was to design the hopper. So you can see here, hopper in this design. So you pour the pellets down into the hopper, and a couple of unique features about the hopper. It's got the acrylic sides, so you can see in there, and then it has the front and the back. And then that is connected to the chute, so that the pellets can run down into there and into the funnel. So it has that interaction with the funnel. The design of the funnel is pretty simple and straightforward, and it has the interaction with the pellets in the barrel, and then of course with the hopper and the chute. So, I said that. Then I'm going to turn the time over to Michelle.
Okay, the last part of the design is the frame, and here's an image of the first model. And we always used, we decided from the beginning to use 80/20 aluminum extrusion because we have that material available to us. In this model, we have it all enclosed because mainly for the B factor so that no one would put their hands in to get burned. And the back panel would flip up with a hinge if we needed to get in there for maintenance reasons. But then when everything was being assembled, we decided to open it up a little bit. So because of our clamping design, we need to bring the mold out and push it back in every time it's used. And so we opened up the front and the top so that it is easier. And like I said, we used aluminum extrusion, which includes the 1.5-inch light extrusion, the angle, T-bolts, and the plastic handles, all available to us, donated. And we also chose this because it's easier to assemble. It won't take as much time once we have all the parts ready. And we used the acrylic sheet so that we could see inside the machine as it's being used. And we've been asked that if the acrylic will have a problem, since it is plastic and it is a plastic injection molding machine, it is not close enough to melt in the process. And we chose a vertical design for the frame, first because of the smaller footprint can fit on the shelf where it's going to be stored, and the gravity aids in purging and injecting, and also because of our bench test, that's how we were able to test the process. We didn't know how to test it in a horizontal position because we used the arbor press. And there's a con, it's not as stable, but if it is connected to the table, it should work fine. Yeah. And in the end, this is our final product, and we would like to open up the time for questions if you have any.
Brad,
Yeah, go ahead.
have you played with that one yet?
You know, we did, like we told you when Jake ran it, we all got together at the beginning of the semester and Jake ran it, but no, I haven't myself pulled the shot.
The only person yet on your team that's pulled a shot has been Jake.
Yes.
Okay. Do you see, and this is where I'm going to lead to a question, as designers, do you see a purpose in knowing the process prior to designing?
Yes. So you're asking why we didn't shoot it ourselves? Is that what you're asking?
You have to ask the question.
Yeah, well, the answer to that is, I mean, if you're working in industry, you consult with professionals that know a process. And Jake is the only one that had been through the plastics class, and so we went with him, and he shot quite a few, so we felt like that was, we understood how the machine worked from that.
But you didn't get a chance to actually
No, we
feel
did
the
not
pressure, what it takes to actually get the shot in there. You say 10 pounds. I don't know if you've actually felt the pressure to actually move that.
Well, we measured it with a fish scale on the bench test. We all were able to shoot a shot yes on the bench test, but not with that machine. So,
Now you said 10 pounds. I saw 20.
well, okay, Sarah, go ahead.
10 pounds is what we found was the value on the bench test. We designed around the 20-pound pool, knowing that we were capable of the 10-pound. The 10-pound was very light. You hardly felt like you were even pulling on it. You couldn't really tell what was going on. With a 20-pound pool, you'll know that actually something's going on.
Well, and, sorry, you'll also notice that we use an arbor press, which uses a gear, which is gonna reduce how much you're gonna have to pull. There's less restrictions, stuff like that. And we went with the cantilever, which we figured would take more to pull than an arbor press.
I guess what I'm wondering is, so every time you want to mold a part, you've got to apply 20 pounds of force to the end of the handle? Is that
Yes.
correct?
Correct.
Okay. You don't think that's excessive? That seems excessive to me. That seems
Well-
pretty high.
Well, Jake, you explain to him about right now how much force it takes to move that, since you're the only one on the team that's done it.
How much force it takes to actually move that?
Yes.
Just, I don't know, probably about 10 to 15 pounds, I'm guessing, when you pull it.
I don't know,
For the
this
plastic
is something
eye.
they're immediate test, I'm just asking them.
Well, I'm just thinking, I think if you're going to require a person that's going to operate this thing to pull 20 pounds, depending upon where that's positioned, that's a lot. I just think it's excessive. I'm saying, I'm wondering if there's a way you could maybe improve that mechanical advantage, but the way you answered that question was it was almost like you wanted it higher because 10 pounds didn't feel right?
Coming from kind of my background is where I've been from.
Sure,
you
I
want- you
don't
want-
know, I just,
Yeah, no, it's fine. You kind of want to know when something's going on. You don't want it so easy where you don't know anything's happening. You don't want to feel like there's nothing in there when you're pulling. You want to know when you're full, when you should stop. The 10-pound force, I mean, all it was basically just a pull like that. I didn't even have to put anything behind it. When we pulled on the fish scale, we used a fish scale on the end of the lever, and the bench test to find that design.
I guess I'm still not understanding. What's the cycle time on something like this?
Cycle time on this machine,
Yeah, how fast can you run the complete cycle to make a part?
Well, if you're
Depending-
talking, sorry, go ahead.
Depending on the mold, usually just, waiting for the plastic to melt usually takes a couple minutes, and then pulling it down is pretty much, 30 seconds from when you pull it down and to cooling time.
So I'm just thinking about fatigue of somebody who's operating. If I had to operate this thing all day long, how often would I have to apply 20 pounds worth of pull? So that's what I'm just wondering if that's.
I don't think that machine's meant to operate all day long. It's meant to be
just
set in a lab
little
situation.
One-off type
So,
of thing.
yeah, one-off is what it's going to be,
It
so.
needs to use, and
So maybe your
Right.
number of 20 pounds is good.
the requirement we came from our customer, George, was to use for the class, for the labs, and as a demonstration when students come through from the high school and take a tour.
I'm just thinking if you have, a brute like Brad, running it up, but if you have some wimpy professor like
But
me.
the second question was, Joe was out the other day, and I was asking how much force would that take before it breaks? Because he's grabbing on, like most people on this one right here, before plastic melts, they grab and they hang onto it, and they want to lift themselves up with it. That's
Oh,
what I was
oh,
trying to get
that
to
was
use.
the
When he
patience
used it,
part
yeah,
you're
I hear
talking
Katie, when
about.
he used it, he was grabbing and trying to lift himself up with it.
Yeah.
I can tell you, it's not 10 pounds of force, boom, it goes right down. It doesn't do that, does it?
Once
Not until
once
it's
it fills
melted.
the mold,
Not
then.
until it's melted.
Patience.
Yeah, you
Then-
hit a
then it
stop,
stops.
you do hit a stop.
And then you have to hold it for an X amount of time to let it cure. But I can tell you, you probably lifted yourself trying to do that. And that's what Joe was doing the other day when he's playing with it without having the motor on, or without the heaters on. He grabbed it, well, trying to lift himself up with it. And he goes, it isn't moving. So now this is a student situation. How much force will it allow before someone breaks it?
I knew you were going to ask that because you asked it the other day. I hadn't had time to do the analysis on it. That's something that I'm going to be doing over the summer, is find the analysis on it and see if we need to change the design, or just alter it, or if it's going to work. That's something I'm going to be looking into.
Have you looked into the possibility of putting like an air cylinder to push it down in so that you wouldn't have to rely on leverage and force, and it would be consistent speed and pressure that you could control?
When we talked to George about it, we suggested that, and he requested that we do it hand operated, so that's the reason we went with that.
And that's because high school students can actually feel something going on.
Yeah.
We do got the two Morgan presses that have the air already out there, so more of a,
But
someone
also,
having physical contact or something.
when we did research, we saw some online that were for
I know
first
you have
article
that.
parts, and they were similar to our assembly, but with an air cylinder. So there exist machines out there, just like you described.
Is there a specification for temperature and pressure for the different materials that you would spec that you're going to be able to shoot?
Yeah, there are. They range anywhere from 300 to 450 degrees.
In temperature, what about pressure?
In pressure, we looked up, I don't have that number off the top of my head, but we referenced 3 different plastics books from different classes when we were researching that to figure out what wattage of heater we needed to get and stuff like that. So I could get you those numbers, I just don't know off the top of my head.
Well, I guess my question relates to what they're asking about is the force requirement. Obviously, if you get a longer moment arm there, the less force you'd have to push. But if you knew exactly what pressure requirements you had to shoot the range of materials you're going to shoot, you could then very specifically decide what force you wanted to have to push, or range of forces you'd have to push, because of the mechanical advantage you've got in your arm there. So it wouldn't be any guessing. You'd know exactly what those ranges are.
Well, and we did, in the bench test, we used all 3 materials, and we used the fish scale to measure as we pulled all 3, and they were they were around 10, they were anywhere from like 8 to 15 pounds, and depending on who was pulling it.
If I ran it at 10, what's the PSI, or what's my injection PSI?
80.92
Was that 80 point
PSI.
something?
Yeah.
Okay, and, okay.
And that was on the arbor press, so using a different lever, the pressure's probably going to be different.
So if you calculated with your moment arm right there, what your actual pressure is going to be, because your pressure, your pull force is completely different in this design than your bench test, correct? Because you were using an arbor press to press completely straight down with it, and now you have a completely different moment arm. Have you calculated it with this design?
We have not.
So it may be different.
Yeah, once again, that's something that I'm going to be doing over the summertime.
And I suggest play with that for a few minutes.
We will. I think
And then see how it feels, because really what you're doing is developing that in a little better form.
Yeah.
Is what appears to me. It's not taking what the other Hanson project was a little bit different. You got a different type of leverage on there. He has a huge leverage arm.
Yeah, he is.
And that's why it's so long, because he has a huge leverage arm, so he puts zero force on it. He's probably trying to get 1,100 pounds out of it, PSI. What, really what maybe, what you probably won't get out of this particular, element across there. So play with it and see what you really are getting. That's one suggestion.
And I have a question more like, how does the student know when it's ready to actually inject? Or is that part of the purpose, that you can't push on it until the stuff's melted? I mean, when it's melted, then you can apply 20 pounds and it goes. I mean, you have a light like a waffle cooker.
Yeah, like on this design here, we're going to do similar to this. I've got a relay in here that when the thermostat's up to temperature, it turns the light on.
Very similar to that one.
And so it's similar to that one, and we're
Okay.
going to use this same design.
Good. That's a good question.
That's really good.
Yeah, that's
I
a
didn't
really
ask
good
that.
question.
That's a good question.
What kind of material are you using on your collars?
the collars, we're using a 304 stainless steel,
Okay.
just to reduce the heat transfer.
Okay, so you've thought about that.
Yeah, I was gonna, let me get another question on here. You guys get bored of these fellas.
No, it's okay. We're having all kinds of fun. This is
Okay,
like one of
I
the
suggested 4130 or 4140, right, for the barrel. Do you know why?
because you asked us to.
Now, do you know why? do you know the purpose behind that?
I don't know.
No, sir.
Okay.
Would you like to tell us?
What type of still is it? Do you know? See, not designed blindly. So maybe you need to look that up and see why. And you might, as well as 4140, you can go with 4130, you know, but there's a reason behind that. The question is, why would I choose that steel instead of aluminum, for example, or a 1020 steel? Why do I choose that particular material across there? Do you have a guess? What do you think? What would be my worry about the material?
Probably the thermal conductivity of it
And the wear.
and the hardness and wear.
Okay.
Because the plunger's going to be going up and down in that barrel so many times that.
With the plastic being very abrasive,
Yeah.
which you should have run the plastics class, the plastics are very abrasive. So why 4140? And now I want you guys to look that up. I'm not going to tell you. I want you to look that up and be prepared to answer that question again.
Okay.
I want you to know, just don't believe me. Believe me, everybody knows here not to believe me, is that right? Anything, don't believe George.
So are you also asking what is 4130
Yeah,
and
exactly
what
what
is
it is.
4140? Not only why did you choose it, but what is it?
Yeah, what is it? And why was that a good still for maybe this application?
Do you know?
No.
Does it have something to do with the pores?
It's,
Like, so that the plastic wouldn't...
Not very porous at all.
too much?
No, that has nothing to do with it.
if Professor Magna was in here, he'd be disappointed in us because we're in materials
I'm
class.
just trying and the other thing I worry about, I think you have the handle and the lever, all 304 stainless, and I don't know if you need to deal with the cost of that. Do you really need a spin? Because that's expensive material. Can I get away with 1018 there? I'm going to ask you that. The thermoconductivity, much difference between the stainless to the carbon material? A little bit, but is it something I'm worried about way over here where I got a handle that's 15 feet away? I don't know. I just don't have you guys look into that as design. I'm not going to rip at it, but I want you to look at that because the answer was heat transfer. So I'm going to ask one more question. I'm going to quit because I can talk about it later on. Barrel size, barrel diameter. Okay. And with the way that you're dealing with the thermal couplings that you're dealing with in the heat bands. And this maybe Jacobs, he's the only one who's had the plastics class already. Why were you scorching the outside of the plastic and not melting inside of the plastic? What's happening there?
With that bench test, with the heat transfer of that aluminum, it transfers so quickly that a lot of times it was just heating the outside of the barrel and dissipating, and the plastic touching the outside of the barrel was melting and staying melted for a long time.
From the 3350 class, how about the plastic?
The melting temperature of the plastic is probably for polyethylene, I believe, is 350, and the barrel probably got too hot, which caused the plastic to scorch.
It's called, what's the proper word for that?
Degrading.
Degraded, right? What about thermoconductivity of the plastic? What's happening there? What's happening in the barrel? What happens, and you don't have to answer, and you have to think about that, because certainly there's a reason why they're going with a small diameter with this. But think about that too. Think about what's happened to the plastic and its thermal conductivity. Okay, I want you guys to think about that. That's all I was going to say. So, I can talk about it all day, but I don't want to do that.
Go ahead.
Just glancing through your drawings, it appears that everything's just defaulted to two-place dimensions, which seems in some cases might be not high enough resolution, not high enough accuracy for what you might have in some of the major parts, but yet even the angle dimensions were two-place dimensions, which say, wow, that's pretty high tolerance for an angle. Have you taken a look at tolerancing, taken a look at dimensional standards to ensure that you are consistent and make sure that other than just your team is looking at the drawings, say the customer?
There are a couple that do have more tolerance than that, like on the clamping system, on the bushings that I made with the rods and stuff. They've got, we looked up a they didn't all get on there. If we could show you our schedule, we have a few more things left to do on the design, specifically tolerancing was one of them, and we've got it on our schedule to have that finished at the first day of next semester. So we've got the summer to shore up our drawings, and that's what we planned for. But yes, we do have that in mind. Glenn, you were raising your hand?
Yeah, I was just gonna say, I like your design, I think it looks really good. I noticed that throughout all your drawings, it looked like there was at least each person's name on at least one drawing, so has that gone okay as far as making that whole thing merge? In terms of you got 5 people with their finger in the pie.
My job was to do the assembly, to get everybody's parts, and that's was a big problem. Mainly because everybody kind of had their own idea on how to do their drawings, and with the first design of the frame, we found that it was extremely big, so we pretty much had to revamp that whole thing to kind of shrink it up, and that kind of messed up everybody else's parts. So my main task
That's why
was,
we've run into the summer a little bit on just finishing up the drawing.
I think, I agree with what Kelly was saying, I would take a close look at your tolerancing, apply it where it needs to be and omit it where it doesn't need to be applied like that. I think the way you've got things organized looks really nice. It's like, I know you've done a ton of work because you've been camped out in that office the whole semester, which is a good thing. I think your logo is great, I think that's nice. And just all in all, I think it's a really good presentation for first semester. One thing I would probably suggest is when you present the next time, maybe not so many times up and down, up and down, up and down, up and down. Kind of maybe make that to where you go and then you go and then you go and then you go and then you go.
It was just hard because we all worked on like every
Sure,
aspect of
sure.
the project.
Yeah, I understand why you did it that way. I'm saying maybe next time to improve your presentation skills, just maybe consider 5 bigger chunks of time rather than 25 little teams.
I just had one other thing. Are all your support structures for the barrels, have you designed those to be stainless at this point?
correct.
Because just given the cost of stainless and all that support structure, I would give you a suggestion that you put an insulator between the barrel and your support structure, and then you could just use mild carbon steel. Just stop the heat transfer there, and then use a cheaper product for all that
We can use
support.
like phenolic or something.
Yeah.
All kinds of things. That's what I was suggesting.
That would
is
cut the
we're
cost-
remove the cost from that.
Cut the cost way down.
Yeah.
And stainless is kind of hard to work with and drill and
It is.
all that as well.
That nickel in there makes it tough. Yeah, great. That's what I was trying to.
Go ahead.
The hopper, is that a custom hopper or?
That we got off of an idea online, so yeah, we just.
It's gonna be a purchase
So
part.
you'll
Well,
machine
no, we'll
it,
make it.
you'll machine it.
You're talking about the hopper,
That white piece.
The
right
white
there.
piece.
the funnel, that's the funnel.
Are you gonna buy the funnel or make the funnel?
We've talked about both, but we've talked about making it. So we're getting towards that,
Out of what?
so. I have to look into that more. I haven't decided.
And then just learning from experiences last semester, I would look at getting something that you can buy off the shelf.
That'd be nice, huh?
Very nice. And then when you're changing angles from your initial hopper going into the funnel, you're going to have some buildup problems right there. So I would look at keeping that angle the same.
We're melting plastic here, we're not making flour.
Yeah.
That grain just doesn't flow.
It does not flow.
It won't flow. If I use regrind on that, then you may want to try the faux
Yeah.
regrind. Go grab my regrind down there. You're gonna have the same type of problem.
Yeah.
So, I mean, you could simplify that design a lot.
The key point, think about the Morgan presses out there and how do we move that plastic?
Yeah,
We keep shoving it, because it doesn't flow.
yeah.
You know, that, and as soon as those pellets get warm, like on that one, it doesn't flow. It's get a toothpick and shove it in there.
That might be something you include in your kind of bench testing type stuff before you get too far through the design, so, because you guys had some significant problems with that, right? Yeah. He knows what he's talking about. I'm just here for the entertainment value.
The shape.
Vibrator.
Yeah, a vibrator.
I have one final question.
Okay.
What is your final favorite color? No, I think you guys did a really good job for
Yeah.
first semester. So.
You did, yeah.
It's a ton
I
of
think we
work,
should
and
give 'em a
it looks
hand
like
and let
it
'em go.
very,
Yeah.
very exciting.
What? Capital, sir, yeah.